Hello everyone, this is Yufei Long, a PhD student from Purdue University. The title of my presentation is Multiscale Simulation of Deployable Composite Structures. This work is done with the cooperation between Purdue and NASA Langley Research Center. The deployable composite structures considered in this study use thin-ply high-strength composite, or TP-HSC. The ply thickness of this composite is much smaller than conventional composite, and their laminates only have a few plies. These deployable structures are widely used on small satellites, as they can be packed into a small volume during storage and deployed into a large ship. But this also means the structure needs to go through large deformation, and long storage time can also introduce time-dependent behavior. To analyze these composite structures, both experiments and simulation are studied. This research focuses on the simulation, and the first simulation we have done is the simulation of column bending test, the CBT. The CBT is a major experimental method to study the bending behavior of TP-HSC. By simulating the CBT, we can verify the material model for further analysis. Then, we can also do a simulation of a deployable boom structure. This structure contains a lenticular boom and a hub, and we can simulate the coiling and deployment of the boom so that the influence of large deformation and long storage time can be analyzed. The simulation framework in this study is based on MSG, which means Mechanics of Structure Genome. The MSG is a generalized homogenization method proposed by Dr. Wenbin Yu. The focus of this presentation is structural simulation, but before that we need to start from MSG homogenization. To do so, we first need to identify the structure gene, or SG, which is the smallest mathematical building block of the structure. It is related with the geometry and also the materials. Then we can do the homogenization using an MSG-based code called SwiftComp to obtain effective properties. The effective properties are implemented into a user subroutine, and along with the finite element model, structural simulation can be carried out. In this study, we are using abacus and shell elements, so we will have the effective ABD matrices implemented in UGES. The material model in this study is viscoelastic with direct integration implementation. In this case, the force and the moment increment are calculated based on strain and curvature increment, ABD Poynting series, and also the loading history. First is the CBT simulation. In this simulation, we use 4-noded shell element to represent the specimen, kinematic coupling for the loading arms, and the reference point for the loading head. The specimen has 4 plies of ± 45 degree plane wave composite. General static step is used on all of the 4 simulation steps, which are the folding, relaxation, unfolding, and recovery. Step time of the 4 simulation steps are shown here. The time of the relaxation is 6 hours, and the recovery is 2 hours. During the experiment, it is observed that the deformation generated by the CBT is non-uniform. This feature is successfully captured by the simulation. In addition, we also found that not only the curvature, but also the moments are non-uniform in the specimen. So to have a direct comparison with the experiment, we need to have some data reduction. Here we use this formula to do the data reduction. They can be considered consistent with the experiment, as we use the rotation at the reference point to calculate the curvature, and the load at the reference point to calculate the moment. We also calculate this effective bending stiffness, D*11, to compare with experiment. Here are the results after data reduction. This plot shows the curvature during folding. We can see that simulation follows the same trend as the experiment, and the magnitude is very close. This is the D*11 during relaxation. We can see some underprediction, but compared with the difference between the experiments, the simulation can be considered accurate. Then we have the curvature after relaxation. Though the viscoelastic material model with direct integration implementation can predict some residual deformation, it is too small compared with the experiment. Since we can see that the difference between the simulation and the experiments are relatively constant, we believe it is caused by the plasticity, which is not included in the current material model. The CBT simulation also has the potential for material calibration. Here we have a demonstrative example for calibrating the D11. Notice that this D11 is different from the D*11. It is the term of the D matrix defining the sectional bending stiffness of the shell element. The optimizer is Dakota. It directly modified the U-gens based on the comparison of D star 1 during relaxation. The error is evaluated using the error sum of squares, the SSE. Here shows the result of calibration. We can see that after the calibration, the material relaxes faster and follows closer to the experiment. And after more than 400 iterations, the SSE is reduced from the initial value of 19 to 3. Now we can look into the simulation of deployable bone structures. Due to the complexity of these structures, we have to apply some simplification to help avoid convergence issue. For example, we apply a tension force at the free end of the boom, and also the whole boom is flattened by 2 flattening plates before the coiling. Different from the CBT simulation, here we use implicit dynamic steps with quasi-static analysis. We have developed 2 models. In this baseline model, the tension force and the flattening plates are kept until the deployment is finished. And then we also have an improved model, which is closer to the real structure. We add some rollers around the hub, so that the tension force and the flattening plates can be removed after coiling. The cross-section of the boom is shown here. It consists of 2 shells bonded together along the webs. It has different layups in different segments, with ± 45 degree plane wave and 0 degree unidirectional plies. It also has an adhesive layer at the webs for funding the shells. Here shows the flattening and the coiling of the boom in the improved model. First, the plate is moved up to flatten the boom. Then the boom starts to coil around the hub. The length of the boom allows it to coil about 1½ circle. After coiling, we remove the tension force and the plates. After a storage time of 6 months, the boom starts to deploy. You can see that during deployment, the boom tends to pop out from the hub. This is a phenomenon not captured by the baseline model. After deployment, the boom is removed from the hub and the boom will go through a recovery of 24 hours. Here on the left shows the contour of the residual curvature in the longitudinal direction, the SK1, and on the right we have the curvature in the hoop direction, the SK2. Both of them are the result after 24 hours of recovery. We can see that the SK1 is trivial while some major values are observed for the SK2. Here is the plot of the SK1 along the longitudinal direction of the boom for both the baseline and the improved model. We can only see some boundary effect at both ends. But on the other side, we have the SK2 plotted along the hoop direction at the mid-span of the boom. We can see some major value in both segment 1 and segment 2. The opposite sign is because of the initial geometry of the cross-section. We can also see that after 24 hours of recovery, the residual curvature is greatly reduced. In summary, in this study, we did some finite element simulation of deployable composite structures with MSG homogenization. The CBT simulation captured non-uniform deformation. With data reduction, the simulation achieved good accuracy for folding and relaxation, but underpredict the curvature after unfolding, which is possibly caused by plasticity. We also demonstrated the potential of CBT simulation for material calibration. We also simulated deployable bone structures, including coiling and deployment. With the baseline and improved models, we found that the residual curvature is negligible in the longitudinal direction, but major in the hoop direction, and it can be greatly reduced after 24 hours of recovery. In the future, we are going to apply some nonlinear material model to the simulation to see the effect on the prediction of residual deformation. Thank you. Any questions?